So we're up to chapter 14. We're going to talk about protection mechanisms in Windows. And here's what we've got. The non-executable stack is a main one. Data execution prevention is what Windows calls it. Write or execute is the way all modern operating systems, with the exception for some reason of the Raspberry Pi, operate, where you are not allowed to have a writable section that's also executable. And the stack data protection we've talked about, canaries, and some new ones, stack layout, armored address space, and ASLR, which we have talked about before. Then heap protections and the structured exception handler protections. So there's two kinds of protection mechanisms. There are general protection mechanisms which can add a layer of protection from the operating system that works even if you're running old code. So you do not have to recompile the code, and that's good, but there's only so much protection you can put in to protect old code. All right, and so here's an example C code with a simple vulnerability. It prints out something, and it calls a function here, and the idea is, it's not shown here, but you imagine perhaps that it would have an overflow here. But anyway, if we think of this one without a vulnerability, it just defines some variables, and the standard stack layout is to just put the variables in the order in which they're defined, or perhaps it looks like the reverse order here, but it doesn't really matter. So they define an integer variable, a string, and then an integer variable, and they just put them in that order. And then at the end of the frame is the saved base pointer and the saved return address. That's what a C compiler will do without any defenses. All right, now a non-executable stack will define the stack memory segment as non-executable, which is a permission. And then if you try to inject code on the stack and run it, it won't run. So in order to bypass it, you just have to run code that is somewhere else. For example, using return-oriented programming, where you go to code that has been put there by a developer. You can still overwrite the address on the stack, and the address will still be used to control the address of code to execute, because that's not executing code on the stack. And of course, the whole point of the stack is you can still store addresses and data there and use them, otherwise it would be useless. So there are various types of data, ways to use this to take over the machine. The one way is if you can put shellcode in the data section, finding a variable under your control in there, then you can jump there and execute code if the data section is executable. You can return to libc, which is the C library of basic functions like printf and getS and so on. You can jump to one of those functions and execute a C function call under your control. And you control the addresses. You can put in an address of a library function, and you control the other elements of the stack, so you can put in the parameters of that function. So you can execute a C library call, which the developer did not intend to happen, under your control. So that's good. One limitation is you can't inject null bytes. So if you want to pass a null byte as an argument to some C call, you're going to have difficulty doing that. You can jump to string copy. This is one special case of return to libc. The thing about string copy, of course, is it will take data which you specify in the stack and copy it to another variable. So you can use this to just copy all of your data to an executable area. And when the string copy is done, it returns to you a pointer to the address of the thing it just copied to. So it's very handy. Returns to you the address you want to jump to. So here's what you do to do a return to string copy. You'd have an overflow here in the variable. Then you fill it in with enough padding to get down here to the return address. There you put a pointer to string copy, and then you put in the parameters here. The source data, destination, and destination return. And the source data would point to somewhere where you put your code, perhaps up here, perhaps down there, and then you copy it to this destination address. So you'd be able to create a memory segment containing your injected code that would not be on the stack. All right, return to gets is another way to do it. This will read from standard in arbitrary data and write it to memory. So that's a pretty good idea. And you can, if you control standard input, you can use standard input to feed it in. And so that's the game here. Here you just have to feed in gets and a couple of addresses, and then you have to be able to feed in data from standard input. Return to code is the most common one and the one we've been using in our overflow exploits on Windows, where you're using code that was already put there by a developer of some kind, either a Windows system routine or part of the application. And you can chain return to code, which is what we've been doing with drop sleds, where you use a few instructions here and a few instructions there to piece together an attack. All right. And then there's return to syscall in Linux. You find two arguments and patch them together, and then you can execute a syscall on Linux, which is the way to run a kernel routine. All right, and then there's return to text. You can jump into the text section of the binary itself where the code lives. All right, this is the way, this is, I'm pretty sure, what we're actually using in that Bowne server. We're actually jumping back into one of the routines that is part of the Bowne server program itself. And this is mostly where you're going to find the vulnerable code these days, because the operating system defenses are getting stronger and stronger. All right, you can also jump to the procedure linkage table, which is another way to find the C libraries. All right. One thing that is kind of fun here is the procedure linkage table only includes pointers to the C system calls that are actually used by the program. And there are some very nice capture the flag programs, and I think the EasyCTF, where you actually find ways to include a C library call that was not included by the developer. Normally that's difficult, but there are some tricky ways you can get around to it. All right, and then you can jump to the dynamic linker resolve. This is another way to do it. I think I used a different technique in that one, but here's another way to jump to the dynamic resolver, which will let you reach functions that were not included in the target binary. All right, so as you see, the fact that the stack is not executable does not really mean that I can't inject shellcode. It just means I have to use one of these indirect methods of injecting shellcode, where I use code. I either find a way to write code to some area of memory that is executable, or I build an exploit of some kind out of the code I can reach. And typically what you do is find a way to turn off these defenses with that. All right, so let's take a look at this in C++. And so here is a simple program that is going to print out. This is going, the purpose of this program, it has to have a string variable. Otherwise, the stack protection will not turn on, because the Windows stack protection is too smart, and it does not always put a stack cookie on every frame, but only in ones that look dangerous. So by having a string variable, it will appear dangerous and activate the cookie protection. And then I've added some inline assembly code here so that I can copy EDX to see an address here and print it out. So this is just a way to move something to a labeled object so I can print it out down here. So I have something called D, which I've defined as a data section object. And this inline assembly code copies the EDX value, copies the label here to that point. And it defines a label section. And the point of this is there's a labeled memory section in text, and I'm able to see it this way. There's just one way to see where the text section is. So I can continue this. I can an address in the data section. I can just print out the pointer D, which I defined up here. That's in the data section. And for an address on the stack, I can just use I, which is just this variable here that I defined inside a routine. So it's going to go in the stack frame for that routine. And down here, I'm going to define an address on the heap by just using malloc to reserve some space on the heap and then print it out. So now, then I'm going to print out the current value of the stack. We're going to use this program quite a bit as we go ahead. And this is going to print out a whole series of pointers going one by one through the words on the stack. And we can compile this thing with all the default protections. And then we have this kind of printout where we see where the an address in the text, data, stack, and heap. And here is the stack, including various pointers. And notice that the stack in this case starts with 53, 0053, and here's an address on the stack, and here's another one on the stack. And after that, the text starts with E1. Notice this 53 followed by B1. This is the saved EBP pointing to an address on the stack, and this is the return pointer pointing to an address in the text section. You can spot them by that pattern. So this is the stack frame. And we can run it a few times and see how it goes. So let's take a look at that mem and memn and see if I can do those. I may not have them ready to go, but let's see. If I go here, and I think I can use the ones I've got in this location, 127A. All right, and if I run, here I've got mem. Yeah, that's what I thought. Now that's the mem with a break at the end, but I think if I use mem1, there we are. So let's do this. We'll do this a little later, but it'll work fine for now. Mem1, this clears the screen and then runs this program mem1. And the reason I did it that way is so I can animate it. So if I just run this over and over, we can see which variables change. And this program is compiled in the default settings. So notice at the top that the text in the data section do not move, but the heap and the stack do move. Every time I run it again, those values change. This is one of the weaknesses of address space layout randomization. It does not randomize every part of a program. The text section in particular does not move, so you can use the code the developer wrote in their own program, which is not randomized. The only thing randomized is the heap and the stack. And that's why return to data and return to code work. And down here you have the stack, and the text section is 8D, and the stack section is 4F. So items, words 6 and 7 here are the stored EBP and the stored return pointer. Here's a 2, which is some kind of counter. Here's a word, H-E-R-E, that I wrote, and we'll play with this more as we go ahead. But anyway, that's the first part here. And I've got no actual live students today, so I'm going to skip over the Kahoots. I may look at them later. And let's talk about this write or execute feature. So memory can be writable for places like the stack where you're going to store data and change it, or it can be executable for areas like the text section, but you can't have both. When I was a beginning assembly language programmer in the late 70s, early 80s, I used to write self-modifying code all the time, where I would write code that would modify the instructions, because the old 6502 8-bit assembly language instruction set was very small, and often the instruction I needed was difficult to accomplish. You're not allowed to do that anymore, and it's a pretty terrible idea anyway. Your text section cannot modify during the run of the code. It's executable but not writable. This is a whole lot better so people can understand your code. Self-modifying code is not a good plan, although that's what we've been doing. Anyway, so that's the problem. By making it so every section is writable or executable, but never both, we are not able to inject anything on the stack and then execute it, because if we can write, it won't run. All right, so there was an old system called PAX that was considered secure, but it slowed things down too much. So then there's the NX bit, which is what Windows has called data execution prevention. You can adjust whether you want it to be turned on or off. There's 2 settings in advanced server properties that you play with in the projects. The default for clients is to use it only for essential system programs. The default for server versions is to use it for all programs. And you can adjust it, but those are the defaults, which means your client is set in a sort of legacy mode so that you can run the old programs easily, and the server is set in a more modern mode where it will often require later versions of programs, but be more secure. So you can still do return to code because the code is in a section that is executable, and some memory might still allow you to reserve these sections. So there are limitations. You can, of course, also turn it off. There is a library called set information process with parameters that will turn it off. But in order to execute that, you have to inject null bytes into the parameters, so it may not be easy to accomplish that. You can also call virtual protect. There's another function you can use to turn off this defense. And all right, another thing you can do is you can first write to it, then change the permissions to executable and execute it. Or you can create a new region of memory allocated for your purposes using virtual alloc. And all right. And then there's stack data protection. Canaries started with stack guard, then went up to pro police, also called stack spacing protection. And they work by just adding this canary value. It's shown here in blue. So you store your local variables, then you put in a canary, and it protects the saved variables and the saved EBP. I think, all right. The original version only protected the return address, but not the EBP, which was not so good. And the later version, which is used in the modern versions of Windows Visual Studio, protect everything. When they originally started, they just put a null byte in for the canary. But then they decided to go to the terminator canary, which is just a list of characters that terminate things. Null byte, carriage return, line feed, or else it's the other way. And this is the end of form or end of data feed. So the idea is they will stop almost any attempt to inject that code. But eventually they settled on just using random values there. All right, another thing is the ideal stack layout. It relocates your local variables to try to put the strings at the end, so that if a string overflows, it will hopefully hit the canary and not hit other variables. But of course, if you have multiple strings, you can still have a situation where in a normal situation, you'd have all your local variables here in one string and the canary right there. That would be nice. But if you have multiple strings, you might be able to overflow from one string into the next string, like we did in a very early project, and this defense cannot save you in that case. But it does prevent you from reaching things like the saved return address, which will be used down here and give you direct control of the instruction pointer. All right, they make compromises. As I said before, if the function doesn't have any string variables and it doesn't look dangerous, then it won't protect it. So it only, it does try to be smart about it, which makes me think there must be a serious performance penalty overhead for this. I would think it would be better to just turn it on all the time for every function, but apparently the slowdown is unacceptable. All right, so we talked about this. If you have multiple strings, you might still be able to overflow one string into the next. And if you use data structures where you define this many bytes for a string, then a pointer, then an integer, then another string, then you are forcing the compiler to lay out the memory exactly your way, and it cannot rearrange those things. So then it would be the programmer's duty to consider buffer overflows when designing the data structure, and that's not likely to occur for most programmers. They aren't that security aware when they're writing code. All right. If you define dynamic, there's an allocate that dynamically allocates space on the stack, and those are always on top. And, you know, as we talked about this before, there may be something valuable to the attacker located after the buffer, like the exception registration record, that they can hit even though they never do move all the way down to the canary. ASCII armored address space is another trick. And what you do here is you load all shared libraries in low memory, so all the addresses start with null pointers. That's the point here, because then if you're using a string injection, you won't be able to do much because you can't inject past a null. This is, all right. It's even more effective on big endian architectures. With little endian architectures, as we've seen in some of the attacks, sometimes you can get away with injecting one null byte, and that might be enough. On a big endian architecture, you could not even inject a single address because all the addresses would start with 0. All right, so if you want to execute this Linux command, you can still make one call to system by making the last injected byte 0. All right, so here's defeating ASCII armored address space. You have a structure here. You're trying to pass this address, and because it goes in backwards, 1, 2, 3, 4, you've got 3, 4, 12, and 0 here, and the next null will be pointed. So it will be implied. So you can still point to addresses by putting, because the last null is the null pointer at the end of a string. All right, and the main executable is not moved there. So everything has limitations. All right, and then there's address space layout randomization, which I'll show you in the demonstration. We're going to have a good fun with this. So in the first place, just like all of these, not all code is randomized. Some code is in a fixed location, and in order to do this, you would like to have a register permanently occupied holding the base of everything, and in 32-bit code, that's really expensive because there aren't enough registers. It's probably a lot better in 64-bit code. All right, if you use return to get, you get to put the data in yourself from standard in and put it wherever you tell it to go, and the address application will tell you where it put it by returning you an address, so it doesn't matter if things are randomized. So that's one way to defeat it. Linux gate is another object that has pointers. This is an information leakage vulnerability. If you can find this, which is sometimes placed at a fixed location, it would be a way to find out where the memory is in this particular instance of a running program. And the one that I paid the most attention to in Windows is insufficient randomization. Some versions of Windows under certain conditions had as little as 8 bits of entropy. So there are only 256 possible locations to randomize things. And that means you could just try your attack 200 or 300 times and you'll get lucky finding the code where you expect it to be. As we'll see in the Server 2016, it's not that bad. Anyway, another thing is if you have areas that are all moved together instead of moving independently, then a leak from one area will give you information about another. And you might be able to access the system memory map, which is here. And you can brute force values. If you can try many times, thousands, tens of thousands, or hundreds of thousands, or millions of times, if you're able to try your attack that many times, then you might be able to brute force it. This will require a situation where you can run the attack rapidly, and the process is willing to keep restarting after every crash thousands of times. So that's probably not that often possible, but there might be situations where that is possible. Format string exploits, if you find one of them, they leak information about RAM, as we've seen, and there's a lot of RPC calls that leak memory addresses. If you have multi-threaded applications, then you can make multiple connections to the same application and try to brute force things more often because all those are talking to the same running process with the same random memory address. If you use fork, Unix processes clone themselves with fork, but they don't re-randomize the memory layout. So that may also give you another chance to attack it. And then there's heap protections. We talked about this before. The simplest case of a heap protection is if you free a node, then you try to adjust these pointers to point to the next and previous node. Then if you were able to overflow the data here, you'd have a write operation that goes under your control. So there's a thing called safe unlink, which before it tries to to repair the heap, will make sure that the pointers have proper integrity, making sure that when you go to the next heap and back, you're where you started. And if you go to the previous heap and back, you're still where you started. So that's safe unlink. It's implemented in all modern operating systems for a long time. All right, but that doesn't block all heap operations. And there's a famous document called the Malak Maleficarium with all these fairly exotic, complicated heap attacks. And heap attacks get pretty complicated in Windows. All right, you can also undo safe unlinking to what they call unsafe unlinking, because that tests whether you can go to the next chunk and back or the previous chunk and back doesn't really mean the entire heap is intact. You might be able to carefully overwrite the pointers so that check will pass. All right, there's a chunk on look aside overwrite. Windows uses this thing called look aside list to record the free chunks. and that you can exploit. But Windows Vista and later got rid of it and switched to something called the low fragmentation heap. Microsoft had heap cookies in Windows XP Service Pack 2, but it was only an 8-bit random cookie, so you could just brute force it. All right, in Vista and later it uses an 8-byte random cookie, which is a whole lot stronger, of course. That's a really hard thing. Brute forcing a 64-bit value is essentially impossible. There's not enough time in the universe for that, or close to it. It's 16 billion choices. And Windows 8 added many more protections, heap handle protection and guard pages, many complicated protections here added in the latest versions of Windows. And I'm sure Windows 10 has that plus even more. So there are many more things added here, and this is all because of Microsoft's embracing of ethical hackers. Now, instead of telling them to shut up and trying to prosecute them, they bring them in the fold and pay them money to write good exploits and pay them more money to write good defenses. So Microsoft's heap defenses have gotten very good. All right. So RD-RAND is another issue. The quality of your random number generator is a problem. And how do you know if something is really random? This is actually a very deep, very complicated problem and has led to a lot of security problems. And in order to improve it, modern processors have a hardware random number generator, which should be a resistor with current flowing through it, and the current randomly varies because of the atomic motion of the atoms inside the resistor, and they amplify that to get truly random numbers. But some people don't trust it because they're afraid the NSA might have forced Intel to poison the hardware random number generator, because the NSA was caught actually by Microsoft poisoning the random number generator used in elliptic curve cryptography. So some people would prefer to use some other technique that is not easier for the government to get to. Although it has never been proven that there's anything wrong with the hardware random number generator, but you can't audit the code and check it. So there's a lot more defenses available in Windows 10 to block firmware. Bootkits is one of the ones with secure boot, which required signed firmware to make your Windows machine like an iPhone, where it won't boot up at all unless it makes sure that the bootloader is an authentic Microsoft bootloader, which has the side effect, of course, that it makes it very difficult to put another operating system like Linux on your Windows machine. But it also means you can't put rootkits on it. And there's many other defenses here that I think I'm not going to go through right here. All right, OpenBSD had some old versions of a heap that didn't use linked lists, but later on it did, and improved it. And in general, it's getting harder and harder as the heap gets stronger and stronger to do these simple attacks. Then there's the structured exception handler, which we were exploiting, I think, last time. It used to be for a while that a register contained the address of the structured exception handler, so you could easily exploit it, but that's no longer true. And you can't put the exception handler on the stack either. So that helps protect it, so a stack buffer overflow can't directly hit it. If you compile with safe SEH, then it has a whitelist of permitted handlers determined during a compile time, and you're not allowed to put any address in the exception handler list that's not on the trusted whitelist. So that's very nice. It blocks you from using simple trampoline attacks. If you have not compiled your code with the safe SEH switch, then it won't have as many protections, but it still will have some. And there are exploitation tools. EEREAP reads a memory dump and tries to find the trampoline code. We're using Mona, which does something similar. Here's something that freezes a process, an SEH inspector. These are tools to help you find and exploit vulnerable SEH. All right, so let me stop this one.